like its work has already taken it to milliseconds. So, hey, what is the ticket?
This thing called an optical filter. So, what exactly our project is about is that light encode light into like quantum. The problem is when we take that light and put it into a physical silicon shell, it bounces off and it scatters and then you lose the in the order to overcome that. Something called optical microscopic cavity, which is in the optical in the that happens to trap light very well within its own. And when there is scattering and all, right, with like due to scattering, you encounter noise. And noise is one of our biggest enemies. And in order to reduce the danger of that noise, we are the optical filter. We got with deep code. Decoding speed speeds. Decoding is the process of that scanner using and making space.
Basically, when you things go out of
I wanted to, yeah. uh,
a little all the time.
So basically, in order to like counter that, we mathematically, tune our system in such a way that it counters the noise by um, fighting against the noise. So you guys know how your noise cancelling headphones work, right? Even though there is environmental noise around you, you your headphones, they work around, they send uh, signal, send a sound, which is 180 like it offers the sound wave which is like that's how your translation hearing earphones work. So it's almost like a similar thing. We're using artificial cavity and prevent that noise.
Based on this one, I would basically say, like, say quantum. It's to understand it very, very simply. It involves linear algebra mostly, forming matrices and things like that. And thereafter, the most challenging part for which people get employed mostly, because most of the people don't understand that. Even when some faculties come to me and say, like, let quantum convert. I mean, okay, convert the quantum thing into classical. Then it's not the other way around because it gets that is called measurement. I mean, you might be aware of that one from your first year. Please keep the fears away. We don't work on the fear basis because we understand the subject. So it's our day-to-day subject, as a matter of fact. These kinds of projects relate directly to what happens in communications and things like that. So yeah, he is the senior who's working on the composite software to bring the reference.
Hi guys, I'm Ritul. I'm also a TA on this, sir. We are working on autonomous fuel control of photonic filter-based systems. So basically, imagine you have a classical routing table which handles all your phone calls. Make sure one phone call goes to the other end. Okay. And now imagine the same system working at the speed of light. That is the capacity of photonics right now. And what we're essentially trying to develop is a controller for these kind of systems. Because even in quantum, I mean, in a photonic system, vacuum can get lost. So we're dealing with a system that's sensitive. So we need something more than a classical guy sitting behind a bunch of nodes dealing with, all this going on. So we can really get a base controller all of the parameters have been so yeah, that's pretty much the first one.
So yeah, I mean, if this one comes out probably in relation to this one, I would say like when you say AI-ML project or something like that. So AI-ML project is doing AI-ML project with two practical feedback we got from us. That doesn't actually get your job. What fails you at the job interview is like they actually try to give you a scenario, and you are supposed to map out where to use what. And mostly in PA students, the problems that we have seen and studied when we made our own elective subjects and all that people can't relate the subjects at the end. Like keep on sporting in the class. So you have to relate the subject you have to come up with this whole plan. Once you're out of your classes, no one will take you like, please solve these questions out of this. You should form of the so, now this is
something to do with vibration or something. Yeah, but what is vibrating? The clock is not vibrating.
They're really having an Evil Dead kind of movie.
Yeah, what is vibrating? Sorry? Exactly, cesium atom vibration. But is the atom vibrating? Technically, no. So basically, what they do is they trap the atoms in structures like this. This is called a magic wavelength lattice. So it's a certain wavelength, so it doesn't,
Sorry, we started a little late. Go ahead. They had to go. He created the problem though about the venue.
What?
We all knew that it's in the third floor. Carry on. I'll scold you later.
Fine. So yeah. So the excitation, de-excitation of the atom will cause like it will give out energy basically, and you measure that energy. And these pulses of energy is what your vibration is, right? And that is what we measure to measure your time, right? So using that same measurement, they basically these many vibrations happen in 1 second, and this is the definition of the second, right? But the issue with that is when you're using the magic wavelength platform is basically light, right? It's light and electromagnetic wavelength fluctuations, so that it traps the atom in that spot. You can see it causes peaks and kind of a hole where it goes and sits. That's a trap system, right? And when it goes and sits there, excitation, de-excitation happens. But the issue with this is the light interacts with the atom, right? You guys know photoelectric effect, and there's many more other interactions. There's a whole model coming more. He talks about atom-like interaction, right? Even if you're talking about interactions like that, it causes a lot of perturbation in it. It causes a lot of error. So
which practically restricts how much hertz it should go up to.
Right. So around now, let's say whatever 1,000. I think this was a 11,000. We bear it as 11,000 hertz, the junior's one. So the 11,000 hertz one. The issue with that is there's no issue as such according to the current standards. Still, there's a lot of loss. Over a couple of days, it comes to almost 10 power minus 1 second. So sorry, 10 power minus 9 seconds.
I mean, so practically, it's like you're saying, like you're using a satellite or something which is of a very touchy nature. The application is a very touchy nature. One day after several days, it will make such a fault that you will be making a wrong move with that one, and that will be politically and internationally troublesome. So trying to make that as close as possible that it never fails. The clock never fails.
Right. So yeah, that fluctuation messes it up, obviously. There's also one more thing. There's electromagnetic bursts, right? Now these clocks are used in GPSs and many more precision instruments. CERN has the most accurate clock, but yeah, sure, they use it for a different use case. But yeah, whatever, this clock is there, right? If I basically put an electromagnetic wave, it messes up the whole clock, right? You have to make something resistant to this messing up the situation happening, right? So what we do is, instead of atoms, we replace it with wave packets of light, which basically have this quantum called a k-vector quantum. And we use this wave packets oscillation to measure the clock system, and we've achieved around 60,000 terahertz on a theoretical system. On a loss perturbated system, it will come down to around 20,000 terahertz, I think, but we are still running some simulations for it. Because the lattice system for that will work in a different way, because you can't technically trap light with light, right? So what we are doing is we're using crystals, which you guys probably heard of so many times today that you're probably bored. But yeah, we're using those crystals and making a trap in it where the photon goes and sits technically. And that's where your de-excitation is.
So, I mean, from my perspective, we are using photonic crystals in this project and the one which was related to your the software thing. So the thing is like the punch over here is like, rather than using atoms and all, we are using a man-made structure, so an artificial structure, so which can be controlled more by us. Now, to make that structure more viable, the other project actually using the basic component as the photonic crystal, which you have to make by taking a block of material, put it into, in our case, put it into IISc, make holes into it. And so we said like, I mean, it was long time on my mind, like, can I do it in a flexible manner? Like, turn it on and off and make it. So what we did is like, we have shown like if we take two areas of lights, like 3D areas of lights, and they're crisscrossing it. That area of light itself acts like the crystal. So that paper is also for application. So yeah, overall, what is the, oh yeah, these are the subjects exactly. They put the other way around. So what we have recognized is like very practical. Is like you guys have been scared to the core in your first year about quantum. So we assume that you know mathematics, and we start from that level, assuming that you know some linear algebra, some linear, and a little bit of idea about magnetics, and then we a little bit of idea about circuits and materials. So basically, these subjects are curated in a way that this is real what is required into the semiconductor industry. Because the only other thing that gets you into semiconductor industry is an experience of hands-on, to have made things by your hand, which is obviously not going to happen in our kind of industry, because you need to have a regular interaction with CIR labs for that one. I taught a few years in NIT Sikkim, so I used to handle those exchanges and know that one. That's not going to happen easily. So these have been curated from that perspective, that I take you up from a very novice thing, like where you can see like how light works, you generate this thing, and your subjects are like, so at the end of the day, from its inception, the ESA and these things have been projects. So you make the project, submit with me a report, and on the report basis, I also check you and teach you like how to do academic writing for your future this thing. So when you're writing SOPs, or because that is something I faced myself in the UK, that in our schools and all, we are not taught how to write a proper scientific report. So that is also incorporated in those. So when the time comes, already to submit the journal. So they are also ready to submit a journal paper now. So they are working on a vortex laser. So that is essential for like now it is coming up about in quantum applications. The vortex laser is very useful. People are saying that there are some drawbacks, etc., which we will address later on. So that particular laser is not there in the world in a laser form. They do signal processing to do the vortex. We bring the signal processing inside the laser. So that's the work name. So if you have any questions, discussions, you talk to them freely. I'll just leave the platform over here, because I think it will be more easy to talk to your batchmates and you see. So thank you very much. What is my phone there?
Okay, on a scale of 1 to 10, how good is that? Yeah. I'll say 8. You put in so much work for this one, talk from there. The mic is there, that's right. The phone's the mic. Right. Yeah. You guys can ask any other questions. Yeah, what's up? One ತಗೊಂಡು ಇಲ್ಲಿಂದ
Okay, so few questions. Before if we select electrics and all in this domain itself, what subjects do you think are like important, like we should know, or because I'm uncertain about my interest?
Maths.
Okay, maths I heard from the lecturer, linear algebra and few other things. What about the other subjects?
Which department?
EC.
EMFT.
Okay, and Okay, one more thing. You publish like 4 journals and what's so. How are you getting updates about how are these projects and all working? Like any sites, any YouTube channels? You follow something like that. I just want to know
I
more
didn't
about this
understand the
domain.
question. I low-key didn't understand the question.
Okay, I want to know how do you know more about this domain? What like because
You
if I
read
just
papers, what the papers doing, you see research gaps, you build on that research gap. For research papers, Google
exactly?
Scholar. So then what's the question? What resources do you want? Okay.
I just wanted to ask how do you know more about this domain? Like more, I wanted you to show me exactly.
I if I say Linus tech tips, no, what will? Oh, okay. Anyways, go on. Complete your question. Yeah.
That was the question.
What YouTube channels I watch?
Now we saw it's like now
Kind of
social
personal. Not gonna
media,
try.
like it's around it.
Ah,
Like how do you get to know about that thing?
the project that this exists.
Yeah.
So basically, when you are in research, your main task is to read. Right? You read a lot. You read a lot of papers. You see what is happening in the world. Right? There's some standard set for the whole system. Right? For So whatever domain you want to work in, you see the standards in that domain and see how you can improve the standards and what conditions there are, and see how you can improve them, right? Obviously, you will have some intuition, right? You can think on your own. You know, okay, math looks like this. From what I know, from what my experience, there can be a system built on this mathematics that it evolves into this system, right? If I can build that particular type of thinking, I can obviously build whatever I want. Does that make sense? Or you want YouTube channels? No, people are keeping on saying YouTube. Oh, huh? Okay. See, it's technically not a YouTube channel, but sure, ICTS ka lectures. ICTS lecture series, any one of them, sit, you'll get an idea, right? The idea for the clock measurement system, right, came from a lecture on gravitational waves, which has nothing to do with this, right? But the measurement system ka maths matches the maths for my readout, right? So we thought, okay, this will work. So we have a better loss. Loss as in, okay, that sounds like a very negative sentence, but better loss in the sense a better system where we have lesser loss, right?
When did you start working on that?
Hey, what's up? Come in, come in.
from computing.ai. What do you think, sir?
I'll place the mic. Yes. So we have time to. We have time. 6. Okay. Okay. Yeah. Okay. Sure. So good evening, everyone, and like today will be. Yeah. So like today we'll be going to talk about quantum circuits. So like I'll just brief you. I'll just brief you what we'll learn today. So like first we'll just brush up our linear algebra concepts. Then we'll like briefly look at what a qubit is and what quantum gate does. And then we'll try to like solve a specific circuit with a few gates at the start. Then I'll teach you how to solve any arbitrary quantum circuit. And then if time remains, like we can go with the functioning of Ducho's algorithm. So like before starting, I want to talk something about me. So I am the CEO. Really sorry, but
And can you use some other stuff?
yes, I'm trying to see if you can put another cable. I think he has gone. Yes, sir. So would you like me to try to the different laptop?
Yes, you can. Yes, you can. Okay. Okay, it started.
We try to put on it, but doesn't work. We can use another laptop. Yeah, shared the same, so we tried testing it out. It worked. Yes.
That table length.
Yeah, it should. Yeah. We can. You have to shift your mic also. I say you will keep the table.
You keep it. Shift the entire table.
Just come with me. Because it's it'll be easier. Okay. Let me try something. Okay. Can you just, yeah.
That's it. What? That's it.
So
Hello, Joy, can you hear me?
yeah, so any number in this complex 2D complex plane can be represented as a complex number, and then you have this Euler's formula where if you have a unit circle on this complex plane, so like every point on this unit sphere can be represented by this number iota e to the power iota theta, where like theta is the angle it makes with the x-axis. So basically, if the point is here, so like it will be for e to the power iota, whatever the angle it is making, and that is basically equals to cos theta plus iota times sin theta. Like if you want to prove this part, you can easily do it like this is the where this is theta, this will be sin theta, this will be cos theta. So cos theta plus sin theta in direction of iota. So like cos theta plus iota sin theta. The very basics of a complex number. Then if we talk about taking conjugates, so like if you just multiply complex number a plus iota b with its complex conjugate a minus iota b, so what you get is a square plus b square. And how this is important is, so if you want to take a like a distance of any vector or a distance from of any complex number from the origin, so like it you see like it's a in this direction and b in this direction. So using Pythagoras theorem, so like the magnitude of this should be root a square plus b square. So this is the magnitude or the magnitude of this complex number, and we can see that with conjugates we can actually like find this a square plus b square. So a product of a complex number is and its conjugate pair is sometimes very useful. Then we'll talk about a mathematical object where magnitude and direction you all know are known as vectors. So there are different forms of representing a vector. This is a general form where a vector is a magnitude and has a direction. Also, you can represent a vector using this kind of notation exi plus byj plus azk. And also, like if you want to fix this dimension, so you can just represent it as ax, ay, az. So like this kind of representation, basically you can do as a kind of a column vector, or either you can use a row vector. So like lot of ways to represent vectors, but the ones which will be going to use in basically solving quantum circuits or like in general quantum algorithms is basically this notation of representing vector. So basically this is called a kate vector, where the kate vector is just a column vector and all the values in here are complex numbers. And if you see the bra A, the bra vector is just a row vector, and basically these are like interconvertible into each other by just taking a transpose conjugate of a vector. So what a complex conjugate transpose is? So first, transpose of a, so a transpose of matrix is a very simple concept. where rows become columns and columns become rows. So we have given this a vector as this matrix as an example, where you have this A matrix as A B C D E F. So if you take a transpose of this, the rows will become columns, and the columns become the rows. So it changes to something like this. Taking a complex conjugate is to just take a complex conjugate of all the terms in a matrix. So like we were taking conjugate here, like for A plus iota B, the complex conjugate is A minus iota B. So like if you just combine these two, transpose and complex conjugate, so if you take this successively, so it's called a complex conjugate transpose, but it's not a very difficult concept to understand. It's just transpose and then complex conjugate. So it's also called as A dagger, like complex conjugate transpose, but it's just equal to taking a transpose and then taking a complex conjugate. So then I want to talk a little about linear transformation. So like you must be familiar with these kind of linear transformations, rotation, reflection, scaling, shearing, projection. So basically what you are doing is you are keeping the origin same and just changing the vector, either scaling it or like changing direction of the vector. And with this, this is basically termed as a linear transformation. So like there are different kind of linear transformation which are possible. So like this is a physical meaning of doing linear transformations. But mathematically, if we talk about how can transformations, so basically you have a vector. In this example, this one. The numbers are expanding only in one direction. Similarly, a matrix is a 2D tensor, then a 3D tensor where another dimension comes in, and similarly, you can have n-dimensional tensors. So, like basically, if you want to combine tensors, so like let's say, just giving an analogy, like if you want to take tensor between these two mathematical quantities, so you have to multiply every element with every other element. So like this whole gets multiplied with this whole gets multiplied by this whole gets multiplied by this and this. So you can see like every possible combination is applied to every other possible combination. So if I just take a example using some vectors, so if I want to take a tensor product between these three matrices, or you can say column vectors, x naught xi cross y naught y1 cross z naught z1. This cross is basically the tensor product the tensor product notation. So basically, how this works is you have to multiply every element with every other element. So here you can see like y naught gets multiplied with both of them, y naught gets multiplied with both of them. Similarly, y1 also gets multiplied with both of them, and then you just open it y naught. Quantum gates are basically unitary transformations. So basically, these are the unitary matrices which are getting applied to the qubit vector to change its state. And we saw like these unitary transformations have a property that they preserve the norm, or the determinant of these gates are basically one. So basically, we started with this qubit or multi-qubit state with magnitude one. So what a quantum gate will ensure is it doesn't change the magnitude of the vector. It will change the vector to some other direction, but it will not change the magnitude. Then measurement is just projection onto the basis state. And quantum circuits, if you see, it's just unitary transformations on qubit states. So we'll go through each of them like very quickly. So, like if you talk about the qubit, so the qubit is the basic unit of information processing in quantum systems. So, like it can be represented by like this get psi, or this column vector can be represented by alpha 0 plus beta 1. So like where this you can see like this is also a get vector, this is also a get vector. So like they should be a column vectors of some kind. And like since like it's just one qubit, so we only have two dimensions associated with it. So like we want to take a matrix with two elements, or you can say a column matrix with two elements. So although like there can be like infinite possible ways of choosing what should be the value of 0 and 1, but for simpler cases we use the value of 0 and 1 as like 0 is equals to 1 0 and 1 is equals to 0 1. So basically, if you see, like if you just try to expand this, so your psi will be just, if you just multiply alpha into 0, it will become alpha 0, and there it will become 0 beta. So it will be just alpha beta. So you can just alpha 0 plus beta 1, either we will get a 0 value or either we will get a 1 value. We'll see like why this happens in the coming slide. But for now, like I can also write this equation as this alpha square plus beta square equals to 1. I've just taken a square here. And also I know that probability of observing 0 plus probability of observing 1 is equals to 1, because only these are the only two events which can happen. And like if I add the possibilities of happening these two both, it should add up to 1. So like, can you see some similarities in these two equations? So first of all, like the right hand side of the equation is 1 on the both sides. On the left side, if we see, like this alpha square and this p1 are not related in any sense. So alpha square is only related to this value, and beta square is not related to this in any sense. Beta square is only related to this value. So what we can basically say from this, we can just reduce it from here. Like the probability of observing 0 is equal to alpha square. Basically, I'm taking the mod of alpha square, and probability of observing 1 is basically equal to beta square. So just from this equation, I'm deducing it, like because like there is no relation between p of 0 and alpha square, and beta square. So like only alpha square and p naught are correlated, and beta square and p1 are correlated. So any doubts here? So like this is also called the normalization condition. So basically, like when we have a state vector, so like first what we want to do, if it is not normalized, we want to normalize it. So then let's talk something about the measurement thing. So like if you see this diagram, so like on the first column you have the state, your qubit state. In the second you have the measurement, like the measurement direction or the measurement, you can say basis in which you are measuring the qubit state. So if you see, like if you have a vertical state and you are measuring it a horizontal vertical direction, obviously like it will be appearing in a vertical direction. And if you have a, let's say, horizontal direction, the state in horizontal direction and you are observing it in horizontal vertical direction, so obviously like, you will be getting it in horizontal direction. But let's say you are having the quantum state in a diagonal direction and you try to measure it in this vertical horizontal directions. So like you won't get this state, obviously the angle one, because you can only measure it either vertical or horizontal. So what happens is sometimes you will get a vertical value, sometimes you will get a horizontal value. So what you can basically say is, like if we are measuring in this basis, this vector is in the superposition of these two states, right? So like, and like if this vector is more aligned towards the vertical side, then this vertical arrow will appear more often. If this arrow is more aligned towards the horizontal side, then this horizontal arrow is more probable to occur. Similarly, we take this vector and measure in this, so either we get this or this. And now we take a vertical direction and measure in the diagonal basis. So again, it's not aligning, so sometimes we will get this and sometimes we will get this, and so on. Last example, we are measuring a vertical direction, a diagonal direction in diagonal basis, so we'll get this direction, and there is no superposition here now. So I hope you are getting the analogy of like how measurement works. So we'll move on to the other slide. So there's something called it multi-qubit states, or like when one or like two or more qubits combine, like it's called a multi-qubit state. And basically, how can we find a multi-qubit state is, like if we have two independent qubits, I'm repeating my words, if we have two independent qubits, so and if you want to take a, like if you represent the two qubits as a multi-qubit state, so what you can do is, like you can take a tensor product between them. So like let's say you are having two qubits in 0, 0 states. So like then the multi-qubit state will be represented by 0, 0 or like a tensor product between 0 and 0. So when these numbers are written like together, so it actually means there is a tensor product between these two. So like this will be 0 cross 0. So if you put the values of 0 here, like 0 is 1, 0. So we are putting 1, 0 cross 1, 0. 1 gets multiplied by these two, 1, 0. 0 gets multiplied by these two, 0, 0. So like this is what comes when we basically calculate 0, 0. So if we do the same thing for 0, 1, so now we have this 1, 0 into 0, 1. So if I just calculate it, 1 into 0, 1, 1, 0, 0, 1, and 0 into these two is 0, 0. Similarly, I can do it for 1, 0 and 1, 1. So I'll get these corresponding numbers or matrices. So like one thing to note here is, like if you take a dot product between any of the two column vectors, let's say we take a dot product between these two. So what's the dot product? 1 into 0 plus 0 into 1 plus 0 into 0 plus 0 into 0. So that is basically 0 only. So since the dot product between these two vectors is 0, we can say like these two vectors are 90 degrees with each other, or we can just say they are orthogonal to each other, or we can say these two serves as two different dimensions. Like it's not the case with only these two. You take any two matrices out of these four, so you will always find the dot product between the two to be equal to 0. So what we can say, all the four matrices or vectors are basically 90 degree with each other, or you can say like these are four different dimensions. Like this is the first dimension, this is second dimension, third dimension, fourth dimension. And for a one qubit system, we were having only two dimensions, like 1, 0 and 0, 1. But with two qubits, we are now having four dimensions. Like similarly, with 3 qubits, we'll have 8 dimensions, 4 qubits will have 14 dimensions, and so on. So this will go on. So basically, generalizing. So if we have n qubits, so we will have 2 to the power n dimensions associated with it. Then something called as a block sphere. So you already know that qubit is just a vector with a magnitude of 1. So like can we represent it using some kind of a sphere with a magnitude 1? So yeah, we can. So like although there are an infinite number of ways to represent the quantum state vector, but like this is a standard one, and with time we'll get used to like why it is the standard. So like one of the things here is there are three axes, x, y, and z. On the z-axis, what you put is a 0. On minus z-axis, you will put a 1. And on the x and like this equatorial plane, where you have the xy axis or the xy plane, so you will represent all the equal superpositions of 0 and 1. Like what can be the equal superposition of 0 and 1? Like each of them could be 0 plus 1 by root 2, 0 minus 1 by root 2. Like why there the equal superposition? Because if you see the coefficient of 0, that's 1 by root 2. So like if you calculate the probability of occurring, like of 0 occurring, it should be 1 by root 2 square or just half. Like similarly for 1, the probability of observing 1 is also half. So like this is a state of equal superposition of 0 and 1. And so thus this vector 0 minus 1 by root 2. And so like these two vectors as well, 0 plus iota 1, 0 minus iota 1. So like one thing you can observe from this, like the 4 points on this xy plane, like this is the x-axis, this is minus x-axis, this is y-axis, this is minus y-axis. So like if you want to remember like what lies at what point, so what you can easily do is like first of all like the coefficient of 0 is always 1 inside the bracket. There is always a 1 by root 2 term here, and only the coefficient of 1 is changing everywhere. Rest everything is same. You can see Like every other same thing is saying coefficient of 1 is here +1, here it is -1, here it is plus iota, here it is minus iota. So like something you must remember here, like this is x-axis, you are getting +1 here. Here minus x-axis, you are getting -1 here. Then this is y-axis, you are getting plus iota here, minus y-axis, you are getting -1 iota. So you have seen this somewhere, like 5-10 minutes ago. So we have seen it here. So like on x-axis, you have a 1 value. On y-axis, you have a iota value. On minus x-axis, you have a -1 value. On minus y-axis, you have minus iota value. So that is what is happening in the block sphere. So x-axis, you have this coefficient of +1, minus x-axis -1, plus y-axis plus iota, minus y-axis minus iota. So it actually came from there only. And if you want to like represent any point on this two-dimensional complex sphere as a quantum state, so you can basically write as this cos theta by 2 0 plus e to the power iota phi sin theta by 2 1. So although like you can try to figure this out yourself how this came. I'll just give you an idea like how are we like why are we using the variables in a way we are using. So first of all, you can see like it is making this vector is making the angle of theta with the z-axis. But in this equation, we are not taking theta, we are taking theta by 2. What should be the reason behind it? So we saw that like this is our 0 and this is our 1. If we take a dot product between 0 and 1, so what should we get? 1 into 0 plus 0 into 1, that is basically 0. So what this means is like these two vectors are 90 degree with each other. But if you see in this block sphere, so like the 0 and 1 are not 90 degree to each other. They are opposite of each other. They are just 180 degree of each other. But we want them to be just 90 degree of each other so that they can be orthogonal. So what we just do is just we divide this theta by 2 to make the angles with respect to 180 degree to angles with respect to 90 degree. And also there is this e to the power iota phi term. So basically this is coming from Euler's formula. So basically this is the phase. What do you basically make with the x-axis? So like when we learned about Euler's formula in the second slide, it was the same thing e to the power iota phi, and it was making an angle phi with this x-axis. So like most of the standards have come from Euler's formula only for this. So like not much to learn here, but I just want you to learn the points which lie basically on x-axis, y-axis, and z-axis. So that will be a little bit useful to us while we try to solve quantum circuits. Then quantum gates we already talked about a little. These quantum gates are unitary transformation, which basically preserves the norm, but basically doesn't change the distance from the origin. And unlike classical gates, quantum gates are reversible. And we saw that the inverse of a unitary gate U is just U dagger. U dagger is just a complex conjugate transpose of U. So like two things they can see from this is one, qubits or quantum gates are unitary in nature, and second, they are reversible. So we'll go ahead. So like there are different kinds of quantum gates. So like there are single qubit gate first, which basically gets applied on a single qubit. So like all of them, all of the gates have a meaning with respect to the blocks where we just learned. So that's why I was telling you that you should at least remember x, y, and z axis and what points lie on this. So basically, if I talk about poly x gate, so basically poly x gate is just reflection around the x-axis, and poly y is just a reflection around y-axis. We'll try to see everything with an example. So poly z is just reflection around the z-axis. Hadamard gate, the most famous one of all. So it converts between the x basis and z basis. or simply we can say it changes between x-axis and the z-axis. So that would be more easier to say. The PS gates. So basically that's the rotation around the z-axis. Then rotation gates Rx, Ry, Rz. So if you want to, let's say, like around the x-axis, you want to take an angle theta, or like arbitrary angle theta, and you want to rotate the vector. So then you can use this Rx gate with whatever angle you needed to put in. Similarly, if you want to take a rotation around y-axis, you can use Ry gate, and similarly, if you want to take a rotation around RZ gate, you can use a RZ gate. So basically, let's try to like see what all this means with the help of an example. So you start with this zero vector, so which is currently basically pointing in positive z direction, and then I apply a Hadamard gate. So what applying a Hadamard gate means is, like we saw from the definition is here is like Hadamard changes between x-axis and the z-axis. So like this is our positive z-axis. So if we just interchange the z-axis with the x-axis, so like this vector will now go to the z-axis because we are changing the z-axis and the x-axis. So the vector will now point towards this x-axis. And what point we have here on this x-axis? 0 plus 1 by root 2. So we have converted from 0 to 0 plus 1 by root 2 just by applying Hadamard gate. But basically what it does, it just basically changes from changes between x-axis and the z-axis. So now I applied a z gate. So what a z gate means is, poly z gate is just takes a reflection around the z-axis. So where is our z-axis? Like this is our z-axis, like the dotted line you can see. So if I take a reflection of this vector around this dotted line, where the vector will go, like it is now pointing in positive z direction, so it will go towards the negative z direction. Just taking a reflection around this z-axis, nothing else. So what point comes here at minus x axis? It is 0 minus 1 by root 2. So now you have changed the vector to 0 minus 1 by root 2. And now if you apply the Hadamard gate again, so like what Hadamard gate does is, it changes between x-axis and the z-axis. So like this is now your minus z-axis. So the vector will, if you convert between x and z, this will now go to the minus z-axis. Not z-axis, it will, as it is a minus x-axis, it will go to minus z-axis. And on the minus z-axis, you can see the point 1. So what you have done is, you have taken a state vector which was initially 0, then you convert it into 0 plus 1 by root 2, then you convert it into 0 minus 1 by root 2, then again you convert it into a 1 vector. Any doubts in this example? So with this you can basically see like this Hadamard gates creates a superposition between 0 and 1. So like if we take this vector 0 and apply Hadamard gate on this, this goes to z x-axis, and x-axis we have 0 plus 1 by root 2. X-axis we have this 0 plus 1 by root 2. So what we say that we have taken a 0 and converted it to a superposition of 0 and 1. So Hadamard gate can basically convert the normal basis into a superposition basis. So that's what is what I'm trying to say here. Then let's come to multi-qubit gates. So just for the example, I'm using this C0 gate. So how this works is, you take xy as an input, like x and y are different qubit state. X remains as it is, and like y, you add this x. So basically, this output here is now dependent both on this vector y and also on this vector x. So like this is basically a combination of these two. So like if you see, it's basically not a plus sign, it's a XOR sign. So like because in binary, so like addition is basically represented by XOR only. I'll give an example what it means. So if you take xy as 0 0, so x remains as it is 0, and y changes to y plus x. So y plus x here is 0 plus 0 0 only. Here if you take 0 1, 0 remains same only, y plus x is 0 plus 1 1. Similarly, you take this 1 0, and this remains the same, and y plus x is 1. Now if you take xy as 1 1, x remains as it is, and y is now equal to x plus y. That is 1 plus 1. So in binary, 1 plus 1 is not equal to 2, it is equal to 0. So that's why I use this XOR operation to represent basically that 1 plus 1 is equal to 0. And also I can just simplify this, and like I can also say like this, like if you take two qubits x and y, if the first qubit is 0, you are not doing anything. So like 0 0 remains 0 0 only, 0 1 remains 0 1 only. But if the first qubit is 1, you just flip the second qubit. So 1 0 changes from 1 0 to 1 1. The second qubit flips. And if you have 1 1, so like since the first qubit is 1, so the second qubit will flip and it will become 0. Any doubts here? So now talking something about quantum circuits. So like if you see like this quantum circuits, so you can see like Q0, Q1, Q2, Q3 are just your qubits, different qubits. This is your first qubit, second qubit, third qubit, and so on. So on y-axis you represent qubits, and x-axis if you see, so it's the time axis. So basically you can see here these are the Hadamard gates, or you can just for simplicity now say that these are the Hadamard matrices. So basically what this diagram means is like you will first multiply this Hadamard gate, or you will first apply this Hadamard gate, then after this is complete, then you will apply this Z gate. After that is complete, then you will apply the C0 gate, then you will apply these sort of gates and so on, and then you will measure. So basically that's the idea behind the quantum circuit. So, and few more examples I want to show you before we can go to the blackboard. So like if you have two qubits in state 0 and 0, two qubits in state 0 and 0, so basically combinedly you can write this state as 0 0, or this will be 0 cross 0 if you want to write it as. And if you apply Hadamard gate on both of the qubits, so let's say you applied on the first qubit, it changes to 0 plus 1 by root 2. The second qubit also changes from this 0 to 0 plus 1 by root 2. Now if you combine this, take a multiplication of these two, so you will get a term of 0 and 0. You will get a term of 0 and 1. You will get a term of 1 0, and you will get a term of 1 1. Right, all possible cases you will get here. And if you just try to see, like it looks something like 0 0 plus 0 1 plus 1 0 plus 1 1. So basically you have created a superposition of all possible two qubit states 0 0 0 1 1 0 and 1 1, and you did this only using like a set of qubits initialized as 0, and then you applied a Hadamard gate on both of these. So another example, you take 3 qubits and you apply Hadamard gate on all of these. So like here you are getting a superposition of all the 2-bit numbers, all possible 2-bit numbers. So since you have 3 qubits here and you apply Hadamard gate on all of that, so what you will get is you will get a superposition of all 3-bit 3-digit numbers with binary input 0 0 0 0 0 1 1 0 1 and so on. And also if you want to write this vector as, so you can also write this vector if you want to write in binary, so you can write it as this. So why this? Because if you see like this if you just expand it 0, 0, 0, so you know what 0 is, like it's just a column vector called 1, 0. So you have to take tensor product between the 0, 0 and 0. So what you will get a 8 into 1 column matrix. So that will be basically 1, 0, 0, 0, 0, 0, 0, 0. So similarly for 0, 0, 1, you will get 0, 1, 0, 0, 0, 0, 0, 0, and so on. Like similarly, for 2 qubit systems, we were getting like the 4 values as this. So because the 3 qubit system has now 8 values, so like you will get a 1 value like in each of the case and zeros everywhere. So basically, I can say if I apply Hadamard gate on all the 3 qubits initialized to 0, I will get a equal superposition of all the states. So from this, basically, we can start on the how much time we have. So basically, what we'll try to do is we can we remove this, or like it should be, it should keep as it is. I can do here.
You want to do this like completely or?
Yeah, this is not required.
Okay.
I'll ask the question. So this will I'll ask the question.
Yeah. So basically, I've taught you like the very basics of how single qubit gates and like multi-qubit gate work. So I did not tell you like how to use it. So you can get it intuitively. But now I'll teach you first. I will start solving like some easier quantum circuits. Then I'll tell you how can you solve any arbitrary quantum state, any arbitrary quantum circuit. So yeah. So for reference, I'm writing the 0 and 1 vectors here. So basically, we'll first let's start with few basic examples of how to solve circuits, and then we'll move to a little complex ones. So let's take a 2 qubit system. So first of all, like let me little bit remind you about Hadamard gate. So Hadamard gate like takes 0 and changes it to 0 plus 1 by root 2. It takes 1 and changes to 0 minus 1 by root 2. And if you take about like see about C0 gates, so basically our C0 gate works is if the first qubit is 0, it won't do anything. If the first qubit is 1, it will basically change the second qubit. So basically, like how like we'll just initialize with 0, 0 circuit, 0, 0 state. This will be let's say psi1, psi2. So like we want to find this quantum state after like all the gates is applied, or we want to find this psi3. So like I'll solve this for you, and then you can basically start. So I want you to basically pay attention for this. Like this is the easy one. If you get this, other ones will be very easy. So if I say about psi1, so I have started like this is my psi1. I started with the 0, and here also is a 0. So my psi1 will just be 0, or just you can say 0, 0. Any doubts here? Why my psi1 is 0, 0? Because I have started with a 0, 0 value. So in the next step, between psi1 and psi2, what I am doing is I am applying a Hadamard gate on the first qubit. I am not changing the second qubit. I am only applying in the first qubit. So my psi2 Hadamard is applied on the 0 qubit and the second qubit as it is. Right? If I apply Hadamard gate on 0, it changes to 0 plus 1 by root 2 cross 0, right? And I'll just put it inside this. It will look something like 0, 0. So this is my psi 2. So I'll just repeat what I have done. So between psi 1 and psi 2, I was using a Hadamard gate on the first qubit. So h into 0 cross 0. Second qubit I have not changed. The first qubit basically changes this 0 to 0 plus 1 by root 2, and 0 stays as it is, and then we multiply with the 0 with this. So it will be 0 0 plus 1 0 by root 2. Any doubts here? And now if I talk about psi 3, so between psi 2 and psi 3, I only have this C0 gate. So basically what the C0 gate will do is, basically if the first qubit is 0, it won't do anything. If the first qubit is 1, it will just flip the second qubit. So let's see from this example. This is a psi 2 and we are applying a C0 gate on this. So this is the first part. So if the first qubit is 0, we are not doing anything. If the first qubit is 1, we'll just flip the second qubit. So this is a psi 3. So like any doubts in how I solved this? So like let's try to introduce one more gate here. So basically I'll call, like, this is called poly Z gate, and what poly gate is poly X gate, and what poly X gate does it, if you apply it on 1, it basically changes to 0, or if you apply it on 0, it basically changes to 1, or you can say it's a NOT gate. So you can see, like, it just basically, like, if you apply it to the qubit, it basically flips the qubit every time. So you can call it a NOT gate. Similarly to classical computer, you have a NOT gate here. So like now you know about 3 types of gate: X gate, Hadamard gate, and a C0 gate. So like, can I clear this? So I'll just first change my quantum circuit to little bit difficult. So like, this is another random circuit which I just drawed. So just view. So basically, if you have your copy and pen, you can try to find psi 1, psi 2, psi 3, and psi 4. And after 1 or 2 minutes, I'll start solving this. So like, this is a very random circuit I drew. So basically, if you can solve this system, you will be able to solve any quantum circuit with X gate, and C0 gate. And next iteration will try to like generalize this to like any quantum gates. So I hope the values are clear. This is a H gate, this is a X gate, X gate. These are C naught gates, and this is a X gate.
So initial value for the third
0.
What's the thing output for Adamant gate of the second one?
0 minus 1 value.
0 minus.
You can see it like that. Like 1 is on negative z axis. So if you apply Adamant gate, it will go to minus x axis, and on the minus x axis, it is 0 minus 1 value. So like you can take 1 more minute. So basically, I'll try to solve this now. So you can see psi 1 here is, we started with this all 0 values. So my psi 1 should be equal to 0, 0, 0. Any doubts here? So in the next step, what we are doing is, like there are 3 gates between these 3. First of all, like the first is there is a Hadamard gate. So Hadamard gets applied on this 0. Then X gates applied on second qubit and the third qubit. I can write it as X0. Right? If you expand this, the H0, it will be if you apply Hadamard on 0, it will be 0 plus 1 by root 2. If you apply an X gate on 0, it will be 1. And if you apply X gate on 0, again it will be 1. So if you just write inside it, it will be 0, 1, 1 plus 1, 1, 1. So this is your psi 2. Any doubts? So next step we have to find the psi 3, and between psi 2 and psi 3 there is only a C naught gate applied on the first and the second qubit. Third qubit is not considered. So like the only condition, if the first qubit is 0, we won't do anything. If the first qubit is 1, we'll just flip the second qubit. So here the first qubit is 0, so we won't do anything. And here the first qubit is 1, so just we'll flip the second qubit. So this is just, I think. Any doubts? So next step we have to find this psi 4. So like first of all, like one thing we can see is like X naught is applied on this first qubit. So the first qubit will absolutely flip, and this then you see the second and the third qubit. So what it means is the second qubit is 0, it won't do anything. If the second qubit is 1, it will just flip the third qubit. So like these two actions I can perform together. So 0, like the first qubit, it will definitely change because of this X. And the second qubit is 1, so we'll just flip the third qubit. And here, like the first qubit, we have to flip. The second qubit is 0, so we won't do anything. So this is your psi 4.
Shouldn't that be 0, 0, 1?
Oh, okay, I'm sorry. It is 0, 0. Thanks for that. So this is your side 4, right? So I think all of you can solve this circuit now. So like in the last step, what I will do is I won't change the circuit. I will just change few of the terms here. So so basically you know that these quantum gates are just matrices. Like for a 2 into 1 matrix, like this 0 is you can just see like this 0 is 1 0 or 2 into 1 matrix. So like this is the 0 value. So whatever matrix get multiplied on this should be of like 2 into 2 format, or a matrix with like 2 into 2 elements. So like what I'll get, I'll do now is, so like anyone with what's your name? Anurag. So we'll make the Anurag gate. Okay. So say any value.
7.
7. Say another one.
4. 5.
No, let's keep the calculation a little simple, as it will take a time. So the determinant of this is 49 plus 16. Right? Or should it be 49 minus 16?
33. 49.
Not this, like, because determinant of this should be greater than 7. Okay, let's take whatever what you said, 33. So let's take that. What's your name? Arshita. So let's make a Arshita gate, and we also say some numbers. 8, 9. So for simplicity, let's take alpha only. Here we take root beta. So what I'm doing here is I'm just making this normalized just to make them unitary matrices. And in this circuit now I'll just replace this by Anurag gate and Arshita gate. And here we will let's keep Z6 gate only. So now can you try to solve the circuit? So you have 2 minutes to try, then I'll start doing. Sorry to say, but there should be 65 only. Determinant of can anyone check on internet like what is the determinant of this matrix? Are you sure? So like why I am multiplying it with the 0 matrix is using the so let's put 65 only for now. We'll see why we use that. So this is the last example, and then we can ask for doubts. So anyone with the approach how to solve this? So one thing without doubt should be like psi1 is equals to 0, 0, 0. Anyone got to psi2?
Shouldn't the determinants be 33 and 17?
Yeah, like it shows that intentionally. So you will see after that why I use 65. At start I wrote 33 only, but I changed to 65. You will see why. So basically, if you want to check like how this Anurag gate and what's the name? Arshita. So like how Arshita gate and Anurag gate will perform. Only thing we need to see is how these gates act on 0 and how these gates acts on 1. And how we will know this? Because these two are the matrices. Like we have this EN matrix. So if we just if I just multiply this with a 0, this is a 0 kit, this is EN. So if I just multiply these two, so what will I get? 7, 7, 4, and and the magnitude of this is 7 square plus 4 square, that is 65. So that's why we are having this 1 by 165 here. Just to make this you can say a unit vector, right? Similarly, I can also check like if I multiply Anurag with 1, what happens? So if I multiply Anurag with 1, so I will get 47, right? So similarly, Arshita 0 is equal to 1 by root 145 and it should be 8, 9, right? And Arshita into 1 equals to 1 by 145, 19. So like these are the 4 things which we like all we need to do to solve this equation. So basically, first of all, like if we see psi 2 on the 0 qubit, you have EN gate, then you have a X gate on 0, then you have this ER gate on this 0. So this EN into 0, what it is giving you? This 7, 4. Or you can basically, can you write this as 7 by root 65. Can you write this as this value? And basically now this is your get 0 and this is your get 1. So basically this will get changed to 7 by root 65 0 plus 4 by root 65 1. X0 gets changed to 1, and if you talk about AR0, so AR0 was this number. I can write it as 8 by root 145 0. So this is your side 2. And now what I can do is I can just bring them all together. Like first of all, I should take this 265 and then what I have here is 7 0 1.
Shouldn't 56 also be outside?
56?
56 should also be outside. Right?
Where is 56?
70 to 8.
Yeah. No, it's not a common term. So basically, what you can do is you can try to solve this. Again, just solve this one for you. We have just taken this coefficient outside, and here you have I'm just multiplying this with this now. So this will be 701 plus 411 cross 80 plus 91. This will be, this remains as it is. Let's get multiply, that is 56 010 plus 63 011 plus 4 into 8 32 110 plus 36 111. So that's your full like side 2 term. So if I want to find side 3 now, so what is between side 2 and side 3? Just a C0 gate. If the first qubit is 0, I won't do anything. If the first qubit is 1, I'll just flip the second qubit. So just taking all this common here, 65 into 145. And here if you see, like 56, first qubit is 0, so you won't do anything. 0 1 0. Now the 63 term, the first qubit is 0, so you won't do anything. 0 1 1. 32 term, first qubit is 1, so you will just flip the second qubit. And 36 term, the first qubit is 1, so you will just flip the second qubit 101. So like this is your side 3 now, and like at the last step if you say side 4, so the first term gets like flipped, and you can basically try to solve this for side 4, right? Yeah, so like I think we are short of time and we should finish now. So basically, now if any arbitrary quantum circuit is given to you with random gates like A and AR, but you know like what are the matrices associated with this gates. So can you like now solve any arbitrary quantum circuit? I hope yes. So like if any doubts, we can take up the doubts. Yeah.
Something like a doubt in the lights.
Yeah.
They ask, shouldn't like the matrices AN and AR,
Ah.
shouldn't they be unit matrices in the sense that it should be the determinant divided by the
Yeah, it should be like
determinant into the matrix?
yeah, it should be like one by root determinant only. But with this example, we can see perfectly it is 1 by root 65. So like.
7 4 8 4 8
Huh?
7 4 8 4 8 7.
Then.
Like
If we like do I, then it will become like 36. Yeah. So I can check this and let you know. We are having a problem calculating the determinant. So I'll just check and let you know why it is happening. Otherwise, it should not be root 33. If it is 7447 only, it should be root 1 by 65 because that is what we want. When we apply a into 0 and a into 1, we should get vectors with unit magnitude. So
shouldn't it be 1 by d, not root d?
1 by
D. Because 1 by root d means you will still get a root d on top, right? You try to cancel it. Shouldn't be 1 by d into the matrix because that's the unit matrix.
Yeah, you are saying correct. So basically, I think this is not the determinant of the matrix then. Because determinant is obviously 7 into 7 minus 16. But I think 65 is suiting this case. Might be some there should be some problem with this matrix. It's because we made this random. So maybe this matrix would not exist as a quantum gate. So I think it's just because we made this random matrix. Otherwise, we are good. I'll also confirm once look into this and let you know whenever you are having the next session. We will clear the confusion whenever you are having the next session. Any more doubts? Any questions? So I think we are almost with the time, it's 6:15 almost. So I've been told to give the session till 6:15 only. So I think I'll be good, guys. 6:15. Should we go to some algorithm or something? Ah, yeah. Yeah, nothing would happen. No. They're almost yes.